Hi, I'm Chris Summers with Keysight, and today I'm going to talk about the SONIC-DASH project, shift left testing, and the importance of a behavioral model. The new normal these days is to combine software development and software test into one role. It's really common to do all the testing way early in the process, right from the beginning of code development, and this is a good thing. It's driven by a lot of different things, including time to market needs, efficiencies, economics, etc. And in order to achieve this, it really needs the proper tooling. Software has to change to incorporate testing right from the get-go. And a lot of infrastructure exists to do that, but you have to build that into your own projects as well. This includes test frameworks, source control, CI/CD pipelines, etc. The Dash project has its own set of drivers. We want a definitive model of the data plane to serve as our standard reference. There will be multiple vendors designing their own implementations, and we need a standalone reference which can serve as the golden template. Also, actual implementations on devices like DPUs and IPUs, it can take quite a long time to develop all the software, and even sometimes the hardware is emerging product. So how can we test this right from the get-go when we don't even have the platforms to test them on? And the community needs a common test bed. Vendors need to guard their IP. They may not wish to share the particulars of their implementation, but we still need something that we can all agree upon is a golden standard reference model. So what's the solution? Well, the industry also likes the term these days called digital twins, which is a software emulation of something. In Dash, we have something called the P4 behavioral model. P4 behavioral model is already being used in the P4 community, but we adopted it for Dash to serve as a definitive data plane model. So by writing our data plane in P4, we get a human readable, precise definition of the data plane. And this includes all the packet operations, lookup tables, ACL rules, etc. It gives us a vendor neutral open implementation that's not dependent to any particular architecture. It's machine executable, which means we can actually run this P4 code in software, send packets to it, get packets back, and write verification test suites. And it's a single source of truth. We actually use this P4 code to generate many artifacts, which I'll show in subsequent slides. So I'd like to show some of the work we've done in the Dash community that creates a great software-based DevOps workflow. I'd like to single out the 4 pillars of our SONIC-DASH Community DevTest. We have the P4 behavioral model, which is P4 source code, and this is community developed. We develop features in P4, we discuss them in P4, and we generate many artifacts off of this code. We have a development environment and functional tests. This is a standardized environment that is pure software based. It's easy to use. Anyone in the community can download this project and work with it. And we actually use it to develop the P4 code and test cases. We also have continuous integration. Any code changes that get submitted to GitHub automatically get run in a CI/CD pipeline. This runs the same make and test scripts that the developer uses in his or her personal development environment, but we get a final check and balance before we accept any new code in GitHub. And finally, there are real-world performance and scale tests run on the actual vendor hardware. This will be covered by my colleague Mircea in the next talk. Keysight worked on all aspects of these 4 pillars. I want to look at some P4 code with you and show you how easy it is to express data plane behavior and give you just a flavor. And I'll also use this P4 code in a subsequent slide to show how we generate other artifacts. This particular piece of code has basically a match action lookup table called PA validation. And what this code here says is look for an entry in the table that contains a matching VNet ID and a matching IPv4 source address. If and only if both of these match exactly to some entry, then permit the packet. Otherwise, by default, deny it or drop it. And these entries would get populated by the control plane In particular, the SI interface will be used to program these tables, and the SI interface in turn is driven by the network operating system, in this case, SONIC. So you can see the code is pretty straightforward. This is kind of a simple example, but really P4 is pretty much this simple and straightforward in general. So this can actually be read by humans and executed by machines. I want to show a bit of the P4 behavior model DevOps workflow that we created for the Dash project. Everything is stored in GitHub using standard community workflows. A developer clones the repo into their workspace, which is another way of saying install the project. They can do a normal edit, build, run, and test development cycle. Editing just uses a code editor. Building uses provided make files that are already part of the project. Running the BMv2 is yet another script that launches the behavioral model, as well as Thrift RPC interface. And then test suites are run using a couple of different Python-based test frameworks. Also, in order to speed up development, we've pre-built a bunch of Docker images that are stored in Azure Container Registry. The first time you do a build, the build scripts will automatically pull down a bunch of Docker images, and that makes the actual incremental build time for the developer just a few minutes. So this entire process can be actually done and experienced in literally 5 to 6 minutes. Once a developer is satisfied that their features are working, let's say they've added some P4 functionality and written some new test cases, then the final step is to push those changes up to the Git repo and do a pull request. And this allows the community to review the work and accept it, review it, give feedback, ask for changes, etc. But one of the first things that happens when you push your changes to GitHub is GitHub triggers some actions. And this is a CI/CD pipeline methodology. We automatically detect a change and run this entire build, run, and test cycle in the CI/CD pipeline right away. And these results are available in several minutes. So those results become part of the pull request review process. If there are errors, then of course something has to be sent back to the drawing board. So we've tried to incorporate the modern best practices for software development. And this really is shift left because the developer is also creating test cases and getting immediate feedback on the work. The P4 code generates numerous artifacts. It's a single source of truth to develop and generate several other items that are used in the overall project integration. So the developer writes P4 source code, does a build. The P4 compiler creates, first of all, an executable behavioral model V2 program. This BMv2 simulator is something provided by the P4 open source community. It's existed for many years, and it can run packet processing pipelines at CPU speeds, several hundred packets per second. The compiler also generates P4 info, which is metadata about the P4 program. That P4 info is transformed using code generators into SI header files. These header files are ultimately what we use to integrate with the SONIC network operating system. They form the southbound API to the data plane. These headers, in turn, are used to generate a SciThrift server and client test harness. This can be used to write Python programs to talk the device under test. P4 info is also used to generate a libsci or a SCI adapter library that converts SCI header files and API interface definitions into an actual RPC that talks to the behavioral model V2. In this case, I don't show the detail, but there's a P4 runtime adapter layer. Libsci translates regular SCI calls into P4 runtime, which then programs this particular implementation. A vendor would implement their own libsci to convert SCI calls into their underlying SDK, however that is implemented. Once we have behavioral model and a SciThrift server, we have a test harness. We can run Python-based test programs, which I'll talk about shortly. These scripts written in Python use a framework that allows you to configure the device under test over SciThrift and also control a software-based traffic generator that will send packets to the device. And then we can write test cases that program the DUT, or the device under test, send traffic, and assert pass or fail criteria. If everything passes, then we have a good test case. Now, in the real world, we can replace this simulator with a real device implemented on some SmartNIC-like device, or even in software, and use a software or a hardware traffic generator to do the same tests. So these tests are reusable in a hardware production environment as well. I told you that the P4 code is transformed into different artifacts, and I just want to give you a glimpse of what that looks like. Here's the P4 source code that I showed you earlier, and you see this table PA validation is defined. We have a source code generator that uses template files and substitution rules to create a SCI header file. This is a portion of a SCI header file that defines CRUD accessors for this table. We have create, remove, set, get, bulk create, and bulk remove accessors. These form the definitive SCI interface to this table. I'm not showing all the attribute definitions, but those are also generated as well. And then we need an RPC test harness, both a server and a client. And here I'm showing Python function definitions that are wrappers using RPC, Thrift in particular. These wrappers will use RPC to call all of these SCI headers on the target. So here's a Python library that's generated from the P4 code. The nice thing is the P4 is the starting point for all of this. So you don't have to manually write all this other code that tracks the P4. Automatic code generation produces it all in one shot. I mentioned that we have test frameworks written using Python. There are two frameworks in use in the Dash project. One is SciPTF, and the other is SciChallenger. SciPTF is a well-regarded sort of legacy framework that's been used for Sci testing and Sonic testing for a long time, and it has many hundreds, even thousands of test cases in the community repository. And this combines Python with the unit test library and the SCAPI packet engine. And this is great for software-based testing. You can use a hardware or a software device under test, but the packets only come out at modest CPU speeds, and you don't get continuous streams of packets. And there's no clear way to go from this framework to one that uses hardware traffic generators. So it's a little bit limited. Once you write these tests, you're kind of stuck in the software packet generator world. We wanted to add the capability of easy migration to line rate packet generation without rewriting the scripts. So we adopted the SciChallenger framework as a complement to SciPTF, and we've recently enhanced it with many features to accelerate Dash testing. So instead of using built-in SCAPI packet engine, which SciPTF uses, we use an open traffic generator interface and has a snappy API, which is a Python or Golang library. It makes it very easy to talk to either software or hardware traffic generators using the same script. Open Traffic Generator is a community project, and you can read about it on this website, otg.dev. It's a landing page. We like this approach because you can write your scripts that are scalable from CPU speeds all the way up to line rate, 800 gigabit per second and beyond. We have a software-based traffic generator called Ixiac. It's a Docker container. It's free, and it can run at very high speeds in the tens of gigabits per second. And then we have hardware traffic generators. Keysight makes these. Other vendors are welcome to interface their hardware traffic generators using this same open API. Using this approach, we can configure the software data plane or even hardware data planes on actual SmartNICs, DPUs or IPUs, and run the same tests either at slow speeds or at high speeds. There are many other advantages to using SciChallenger, which I list here, and you can read more about it at some of these links here. So in summary, I've discussed the first three of these four pillars of the SONIC-DASH test environment. We talked about the P4 behavioral model, the development environment, and the continuous integration on GitHub. I hope you found this useful, and I'll turn it over to my colleague Mircea to talk about performance and scale testing. Thank you.